So let's recall what we did in the last class. So what we obtained, so we have this notion of nth order divided difference, right? And we obtained that this can be computed as by the division of these two differences, right? And this how, so what was the definition of this? Like this was nothing but the coefficient of the highest order power, highest order degree in the interpolating polynomial, right? With this data xi's and the yi's ranging from 0 to n, right? So we further we also obtain another characterization of this nth order divided difference through the Hermite-Jacobi theorem, which says that this nth order divided difference, this is given by the integral of nth derivative of f evaluated as this argument, where the integration is with respect to the indices t1, t2 up to tn. And this reason, the reason of the integration is tau n, which is the set of all t1, t2 up to tn, where each of the ti is non-negative and summation of all ti's I ranging from 1 to n, this is less than equal to 1. And then t0 is such that
one minus summation of I equal to 1 to n minus 1 ti.
right. So basically we have that summation of ti, I is equal to 0 to n. This is nothing but 1, right? So note that while proving this characterization, we assumed that xi's are distinct, right? And why that assumption was required? Because the what we know about this divided difference is that this is given by this, and this requires that we are dividing it by the difference of two nodes, right? So while proving this result, we assume that the xi's are different because we know that the definition of this when xi's are different, right? If they coincide, so that's what we are trying to get the characterization that, okay, so at this point, we cannot use this formula if xi's are coinciding, right? Any of the two xi's are same, I cannot use this formula, right? So, but while proving this result, of course, since we know that the formula only for the xi's when each of the xi's are distinct, so that's what the assumption we have when we prove this result, right? But once we have got this result, now if you try to observe, you can use this another characterization of your nth order divided differences, okay? And if you try to observe, if I treat this, the nth order divided difference as a function of n variables, let's call these variables as x1, x0, x1 up to xn, right? And it is given by this, right? So if I treat them x0, xn, x1 up to xn these as a variable, so, and assuming that f is n times continuously differentiable, then you can notice that this integral makes sense, right? Doesn't matter what your xi, where your xi's are ranging from, right? Or whether any of these variable x1 or say x2 or any of the xi's, they are equal or not, right? So this integral is going to make sense irrespective of whether x0 is the same as x1 or x1 is the same as x2 or any two different, we don't have a distinct indices. We say we have two same variables, say x1 is equal to x2, right? In that case also, this integral will make sense, okay? So basically, when your nodes coincide, I'm treating this as a new characterization of my divided differences, okay? Because this integral is going to make sense irrespective of your xi's are distinct or not. Okay, and we can obtain that. So we can obtain one property of divided differences when all the nodes coincide. So we can prove that. So this is an observation. Suppose we take so let xi is equal to x naught for all I ranging from 1 to n. So in this case, what will happen to the divided difference? So here, these are, I'm having it as f of x naught, x1, x2 up to xn, which will equal to this. And if I use its definition through this, which is coming through the Hermite and Janicki formula. So what we have, this is given by the integral over the region tau n and its derivative of f with the argument as t naught, x naught, and this sum up to the tn xn, dt1, dt2 up to dtn. Okay, and where we know that the summation of all the ti's, I is ranging from 0 to 1, 0 to n, this is equal to 1. So if we simplify this, so here we have that all my xi's coincide, right? So this is going to be t naught plus t1 up to tn times x naught dt1 up to dtn. So here this sum is 1. So what we are left with, that this evaluation is only at the x naught, right? So now this is a constant with respect to the ti's, so I can take it out. So the integration will be only with respect to the constant 1 here. Okay, so you have a constant function 1 here, which you are integrating. So what you will get that this is nothing but the volume of the region tau n. Okay, and what this volume will be, can you tell me? Or how can we realize the value of this integral? Okay, so I'm giving you one exercise here. So the claim is that this integral, which is nothing but the volume of the tau n, this is 1 divided by factorial m. So how will you prove this? Or how will you realize this that this volume is going to be 1 by factorial m? Okay, so you have to again, one way is that you can directly use this Hermite-Janicki relation again for a specific function. So if I call this as a formula 1, this is as 2. So if you take, so this is just a hint. So you take function fx to be x raised to power n. Okay, and you try to use the Hermite-Janicki formula.
Ma'am?
Yeah.
Ma'am, can we do it by induction?
Yes, you can do that way also. So this is just one way I'm telling because we have already obtained this formula, but you can do it either way you want to do it. Okay, you can simply realize that you can apply the induction here and that also will work. Okay? So, but I just wanted to point out one property of these divided differences again. So note that we know that these divided differences are related to the derivative of the function, right? So this is nothing but the same as n plus 1th derivative of f evaluated at some j divided by factorial n plus 1, where xi is lying between the smallest interval containing all the xi's, right? So if I take f to be x raised to power n, so what will happen to the, so this is x not up to, no, this is fn. I think nth derivative of f not n plus 1. Okay, factorial n. So now if you take fx to be x raised to power n, you can simplify this side because x raised to power n is a polynomial. You can simply use this formula to simplify this, and then so you just have to realize that the nth derivative of x raised to power n is going to be a constant. Okay, so if you use that, you will be able to get that the volume of the this region tau n is 1 by factorial n. Okay, so this you just work it out. So basically, what I have got here is that this quantity is 1 by factorial n. So we have got this relation. Okay. So we'll try to see some application of this result when we try to take some example and try to see how will you use this result. Right. Okay, and I'm going to leave one more exercise for you. Okay, if we assume that f is n plus 2 times continuously differentiable. Okay, and let's talk about this function. So I'm having the divided difference of f with the arguments x0, x1 up to xn and x. Okay. So what can you say about the smoothness of this function? Because this is again going to be a function of x, right? You can realize it using the Hermite-Jacobi formula. So what can we say about the continuity or the differentiability of this function? So can we say that this function is going to be continuous function of x with respect to the variable x? F is given to be n plus 2 times continuously differentiable. Okay, so if I try to use this Hermite-Jacobi formula, what I will get? So you will be having the n plus 1th derivative of the f with some argument, right? So first of all, how will you conclude that this is going to be a continuous function? Can you just use some basic theorem, fundamental theorem of calculus? What does that say? So if you talk about the integral of a to b fx, this is not some, let's take some different function here, gx dx, right? Let's take a to x gs ds. Okay, and let's define it as a function of x. So what can we say about the continuity and the differentiability of this function based on the continuity of this g? Suppose I assume that g is continuous.
If g is continuous, then f is differentiable.
Then f is going to be differentiable, right? By the fundamental theorem of calculus. So the same thing you can realize here. So if I'm going to treat this as a function of x here, you will have fn plus 1 and evaluate it at some argument which will also contain x, right? And if f is n plus 2 times differentiable, the n plus 1th derivative is going to be, what I have assumed, is n plus 2 times differentiable, right? So the n plus 1th derivative is also going to be continuous, right? So this means that this function which we have here, this is going to be a differentiable function, right? So you can talk about the derivative of this. So this you can use the fundamental theorem of calculus to realize this. So you can differentiate this. So you use the limit definition. So let me call this function as sum gx. Okay, so I will get this as g of x plus h minus g of x divided by h. Okay, you simplify this, and my claim is that what you will get as an output is this. Okay, so this is an exercise, verify. So that is, if you differentiate this function, what you will get another divided difference. So here you have increased one more argument, which is x here. Okay. And one more thing, let's quickly recall what is the Newton's form of the interpolating polynomial, because that we will be using it in further discussion. So this is, can you tell me? Newton's
fx
f of x naught plus x minus x naught.
Okay, f of x naught plus x minus x naught, f of
X naught comma x1 dot dot dot.
And this will go up to
X
the
naught x
is going to be x minus x
dot
naught.
dot x minus xn minus 1.
So the
And
product,
fx naught to xn.
okay, so product is going to be x minus x and minus 1, and then we have the nth order divided difference with the arguments x naught up to xn. Okay. So what we are going to do, so if we assume that my nodes are equally distant, that is, if I take my xi's to be, suppose I have x naught, and then I'm taking that all of my nodes are equally spaced. So x1, x2, x3. So the distance between any two conjugative nodes is the same. Okay, let's call the distance to be h. So that is what we have, that my xi's, they are going to be x naught plus ih. I is ranging from 0 up to n. Okay, so in this case, we can further simplify this Newton's divided difference formula for interpolating polynomial. So let's see how can we do the simplification. So I'm going to use another notion, which is the forward differences. So we will get a new form of the interpolating polynomial, which we will call it as Newton's forward difference form of interpolating polynomial. So which we will see in a minute that what we mean by the forward differences. So what we assume here, that my nodes are equally distant. Assume that the nodes, they are equally spaced. Okay. So I'm going to introduce this notion of the forward differences, and then we'll try to simplify the Newton's divided difference formula. Okay, so if we take any point z, and if we consider this difference, so h is some given number. So for a given h greater than 0. So here, for example, here when we are going to talk about the equally spaced point, h is going to be the distance between any two consecutive points, right? But this I can define it for any h positive. So I can talk about the difference. Suppose you have the function value at z, and then you have the function value at z plus h. So I'm just taking the difference of the function value at z plus h with the function value at the z. And this I call it as, I denote it by delta h of fz. Okay, and this is called the first forward difference of f at z. Okay, and if h is understood by the contest, that okay, which contest we are, so I'm, for example, in this case, when we are going to work with the equally spaced point, we know that h is a distance between any two consecutive points. So I can very well skip the subscript h, and I'm just going to use the notation delta. Okay, so delta, so basically delta h of fz is the same as delta of the fz, which will be the f of z plus h minus f of z. Okay, so this operator delta h, or so-called delta, this is called the forward difference operator. Okay, so for example, in case of the equally spaced point xi, I can write delta of the fxi. This is going to be f of xi plus h minus f of xi, but xi plus h is nothing but xi plus 1. So this is going to be xi plus 1 minus f of xi. And if I just use this shortened notation, fi for f of xi, so I can write this as delta of fi equals fi plus 1 minus fi. Okay, and I is ranging from 0 up to n. All right, so this is how we understand the first forward difference of f at any node xi, right? So we are talking about first, right? So automatically we get the idea that, okay, we should be able to define it the second and higher also, right? So in fact, we can define it rth order forward difference. So let me again use it here. This is space. So in general, for any r greater than equal to 0, which is an integer, we can define delta r plus 1 fz as delta r of fz plus h minus delta r of fz. Okay, and we have the, okay, so we have to set what happens when we talk about the delta 0 of the fz. So this is going to be simply fz. Okay. So this delta r of the fz, this is called the rth order forward difference of f at z. So now let's go back to this Newton's form of the divided formula. So if I want to simplify this, so I know that what are these divided differences, right? So in this formula, we have the f of say the nth order divided difference, right? Starting from the first divided difference up to the nth order divided difference we have, right? So if you want to simplify this formula in terms of the forward differences, we have to get a relation between the divided differences and the forward differences, right? So we can prove that. This is a proposition. We can prove that for any k greater than or equal to 0, the divided difference of f at x naught, the kth order divided difference, this is going to be same as you take the kth order forward difference of f at x naught divided by factorial k into h raised to power k. Okay, so let's give it equation number. So this is, let's call this as 3, and let's call it 4. So let's try to prove this result. So again, we are going to use the mathematical induction here. So let's take the base case. So k is equal to 0. Okay, k is equal to 0. This is both side f of x naught, so it is trivially true. So let's take the base case to be k is equal to 1. So let's consider what is f of x naught x1. So I'm directly going to use its definition. So this is f of x1 minus f of x naught divided by x1 minus x naught. Now, what is this term in the numerator? This is nothing but the first forward difference of f at x naught, right? And we have considered the equally spaced point. So x1 minus x naught is going to be h, right? So this means that we have obtained 4 for k is equal to 1. So now we assume that this result 4, this holds for k less than equal to r, and we try to prove that it is true for k is equal to r plus 1. So what happens for the case k is equal to r plus 1? So again, I'm going to consider the divided difference of f with the arguments x naught, x1 up to xr plus 1. That is, this is r plus 1th divided difference of f at x naught. So use its definition. So what we have, that this is nothing but f of x1, x2 up to xr plus 1 minus f of x naught, x1 up to xr divided by xr plus 1 minus x naught, right? So now what should we do? So we are just going to use the induction hypothesis that the result holds for k less than equal to r. So using that, what can we say to this first term, what it is going to be equal to? So what is the first term? If I assume that this result 4, it holds for k is equal to r, then what the first term is going to be using this result?
Delta RF1.
So delta r f evaluated at x1 divided by factorial r h raised to power r, right? And then the second term is going to be rth forward difference of f at x naught divided by factorial r into h raised to power r. Now what is this difference? This is nothing but r plus
R
1
plus 1 h.
times h, because all the nodes are equally spaced. So if I just simplify what we have got, delta r of the fx1 minus delta r of fx naught divided by, so I'm going to combine factorial r and r plus 1. So this will be factorial r plus 1 and h raised to power r plus 1. Okay. And the numerator is nothing but delta, the r plus 1th forward difference of f at x naught. Okay. So this implies that the result, that is 4, holds for k is equal to r plus 1, and therefore by mathematical induction it holds for any k in n. Okay, any natural number k. All right. So we have obtained a relation between the divided differences and the forward differences. So now to write the interpolating polynomial in terms of the forward differences, I'm simply going to use this formula. So let's call it proposition 1. All right, so now what we are going to do, we modify the Newton's divided difference So we modify the Newton's divided difference interpolation formula to a new formula involving divided differences, forward divided differences. So what we are going to use for that, we are going to use the proposition 1. Okay. So let's see how do we do it. So we have Pnx as f of x naught plus x minus x naught f of x naught x1, and the last term in this summation is going to be x minus x naught up to x minus xn minus 1 into nth forward difference of f at x naught. Got what these divided differences are in terms of the forward difference. So, and we also know that these nodes are equally spaced. All the xi's are equally spaced. Okay, so I'm just going to set a. So let's define. So I'm taking this difference x minus x naught. Okay, let's divide it by h. So let's call it p. Okay, so this is what I'm going to set, where all these nodes are equally spaced. That is, we know that any xi's is nothing but x0. Simplify this formula. Okay, so what I interpolating polynomial, I'll be having the different products, x minus x naught, x minus x1, right? So let me just take this product x minus x naught, x minus x1 for any general k and try to see what happens. Okay, so if I use this, p is x minus x naught divided by h, so I can write this. Okay, let's try to simplify any x minus xi. So what will happen? So x is x naught plus ph minus xi is x naught minus ih. So what I will get? This is p minus I into h. So I will get this product as x minus x naught is p into h, and then p minus 1 up to p minus k h raised to power k plus 1. Okay. So using this, I can write my p and x as, so the first term is f of x naught. Now x minus x naught is p into h, and f of x naught is going to be f x naught divided by factorial 1 into h raised to power 1. Right? So this is using proposition 1. Now the second term is going to be p into p minus 1 into h square, and then delta square f evaluated at x naught divided by factorial 2 into h square. So this will go up to, the last term is going to be p minus 1 up to p minus n plus 1 delta n f x naught divided by factorial n into h raised to power n. Okay, so if we simplify this, so you can see that all these powers of the h are cancelling out. Right, so what we are left with, so again I'm going to use the notion f naught for this. So f naught plus p into p minus p divided by p into delta of the f naught plus p into p minus 1 divided by factorial 2 delta square of f naught. And the last term in this summation is going to be p minus 1 up to p minus n plus 1 divided by factorial n delta n of f naught. Okay, so do you recognize these coefficients here? They are famous coefficients. There's a name for it.
Binomial coefficient.
Yeah, so these are the binomial coefficients. So if you observe these p minus 1 up to p minus k plus 1 divided by factorial k, this is nothing but you can write this as factorial p into divided by factorial k into factorial p minus k. So these are the binomial coefficients. Right? So I can write this formula as, so summation of Pj delta j f naught, and j is ranging from 0 to n. So where this symbol here, so you can use either this bracket symbol, or you can write this p ck. Okay, so I'm just using this bracket symbol. So what we have got, that Pn x has this form. So it is given by j is equal to 0 to n. P choose j, delta j, f naught. Okay, so this is the Newton's forward difference form of the interpolating polynomial. So here P is x minus x naught divided by h. Okay. So basically, if you have to compute this polynomial, you just need to compute the forward differences of the f. So like we have seen that we can divide a difference table, right? So similar way, we can also form a forward difference table. So how it will look like? So for a given data, say we have the data x0, x1, x2, x3. So you can have whatever is the size of the data, you can just write it down. And these are the xi's. And then we have the fxi, which is also given. So let's call them f0, f1, f2, f3. And so this is the way you will have the data given. So now you can find the first forward difference of f at xi's. So let's call it delta fi. So this is going to be, so delta f0 will be f1 minus f0, right? So you just have to take the difference of these two conjugative entries. So likewise, if you take a difference of these two conjugative entries, you will get delta of the f1, right? Which is nothing but f2 minus f1. And likewise, you can find all the first order forward differences. Right. So basically, simply you have to take the difference of two conjugative entries from the vector fi. Now, if you recall, in the case of the divided difference, we were taking the difference of the two conjugative entries and then we were dividing by the difference of the conjugative nodes, right, to compute the first order forward difference. So we have basically, we are not doing the division part now. We are just taking the difference of the two conjugative entries of the vector y. So once you found the first order differences, you can find forward differences by just taking the difference of the two conjugative entries of the first order forward difference, right? So if you take the difference of these two, so you will get delta naught of f naught, which is nothing but delta of the f1 minus delta of the f naught, right? And if you take a difference of the f1. Definition, it is nothing but of the f2 minus delta of the f1. So this is the way you can compute the forward difference table. Likewise, you can compute the third order forward differences, which will be just the difference of the two conjugative entries of the second order forward difference vector. Okay. So let's take one example and try to do it. So which takes the following value. So y at 1 is given to be 24. Y at 3 is given to be 120. Y at 5 is given to be 336. And y at 7 is given to be 720. Okay. So let's try to solve it. Okay, let's add one more part here. So you have to obtain, once you find the cubic polynomial, then you find the value of y at 2. Okay. So what we have to do, we are just going to form the forward difference table and then because the nodes are equally spaced here. Okay, you can observe that xi's which are given to us is 1, 3, 5, and 7. So they're equally spaced, right? And correspondingly yi. So okay, I'm calling yi, but they are, you can take it as f evaluation at the xi's. So they are given to be 24, 120, 336, and 720. Okay. So let's form the forward difference table. So let's compute the first forward difference. So I just have to take the difference of these two consecutive entries to get the forward differences. So 120 minus 24, this is going to be 96. And then you take the difference of this. So this is 260. And the difference of this, if you'll take, you'll get the so 3. And now you can find the second forward differences. So the difference of these two consecutive entries, that will give you the delta square of f0, which is 120. And if you take a difference of these two entries, which is 168, so this will be your delta square f1. And then you can find the third order forward differences. So which is the difference of this. So this is 48. So once we have this table, we can what is the polynomial. So we have that P3x is given by f0 plus P1 delta f0 plus P choose 2 delta square f0 plus P choose 3 delta cube f0. Right? So P is what? P is x minus x0 divided by h. So x0 is given to be 1 and h is given to be, you can take a difference of any two consecutive entries. So x1 minus x0, which is 2. So we have this as x minus 1 divided by 2. So what we get is f0 is 24 plus this is p is x minus 1 divided by 2 and delta f0 is 96. This is p minus 1. So let's just simplify this. So we will get this as x minus 1 divided by 2 and x minus 1 divided by 2 minus 1. And 1 divided by factorial 2. And delta square of the f0 is 120. And the last term is going to be 1 by 6 p minus 1 p minus 2 into delta cube of the f0, which is 48. Okay, so if you simplify this, what we will get, let me directly write it. So we get this as x cube plus 6x square plus 11x plus 6. Okay, and we can use this to find the approximation of y evaluated at 2, which is nothing but this polynomial evaluated at 2, and this will give you, if you simplify, 60. Okay, so this is how you can use you can form the forward difference table, and you can use this forward difference form of the interpolating polynomial to find the interpolating polynomial. But this works only in the cases when your nodes are equally spaced. All right. Okay, so like we have defined the forward differences, right? So there's another notion of the differences which is called the backward differences. So we have a, say the point Z, right? And in the forward difference, what we had done, we moved right? So as the name says here, instead of the moving forward, I'll be moving one step backward. So I'll be going to Z minus H. I'm going to consider this difference, Fz minus F of Z minus H. And this is called the first backward difference of F at Z. Okay, so this is the first order backward difference of F at Z. Okay, and we can define the higher order backward differences also. So if you talk about the R plus 1th order backward difference of F at Z, this is nothing but the Rth order backward difference of F at Z minus Rth order backward difference of F at Z minus H. Okay. So now I'm leaving one exercise for you that you have to find. So you use the backward differences of F to obtain the Newton's backward difference interpolation formula. That is what you have to do. Suppose we are given a notes x0. Note that here I'm moving backward, right? So I have to have the data accordingly. So I'm calling the nodes as starting from the x0. The next node will be x minus 1, x minus 2, up to x minus n. Okay. So if we call any x minus j, this is nothing but x0 minus jh. J is ranging from 0 up to n. So with these nodes, you first obtain the relation between the divided differences of F at these nodes and the backward differences of, so this is going to be, so if I take here K, this is going to be kth order backward difference of F at x0, and you will get some factor. So this is going to be factorial K h raised to power K. So first you have to observe this and then use this in the Newton's form of, so Newton's divided difference formula for interpolating polynomial. To get the new form of the polynomial in terms of backward differences. Okay, So this is an exercise for you. You just work it out. It follows with a similar line what we have done in the case of the forward differences. All right. So now let's try to summarize what we have done so far. So we have been given the nodes exercise, right? And the functional evaluation at these nodes, say yi's, right? So we have been given this data and we have found a polynomial of degree less than equal to n, which basically interpolates this data. That is, this equals fxi at all these given nodes. Right, so this is what we have done. It's just that we have seen different forms of the interpolating polynomial. We can write the same polynomial in the form of the Lagrange. We have a Lagrange form, and then same polynomial when the points are equally spaced, we could write it in using the forward differences, and we can also write it backward differences. So likewise, there are other differences also. There's a center differences. Okay, so I'm not going to go into the details of all of them. I just wanted to give the idea that you can have a simplified form when the nodes are equally spaced. Okay, so this is what we have done so far in finding the interpolating polynomial. That we just what was the idea? We just first realized what is the degree of this polynomial, and then we got a formula for the computing it. So now I'm posing a new problem. So suppose we are not just given the evaluation of the function at the nodes, we are also provided with the information that we know that the f prime at the xi's for all I ranging from 0 up to n. That is, we know the functional evaluation at the nodes, and we also know the derivatives of the function f at the xi's. Okay, so the question what we are posing now, that can we find a polynomial, let's call it px, which will interpolate. So this polynomial is such that this interpolates fx at the nodes xi's. Okay, and if we take its derivative, that is p prime of the x, this will interpolate the derivative of f at the same nodes xi's. Right? So we are going to find such polynomials, and this process is called so this polynomial which we will be finding is called the Hermite interpolating polynomial, and this process of finding is called the Hermite interpolation. So let's try to understand how do we find such polynomials. So let's pose the problem properly first. So we are given the set of data points. So let's call them yi's and let's call them yi prime. So when I write yi prime, it's not the derivative. Okay, it's just a notation yi prime I'm calling it. But when I write it with the function f, it is a derivative of the function f. So given the set of data points, we have it as xi's, yi's, and yi prime, where I is ranging from. Okay, so I'll just try to be consistent with what we have in the book. So let's start with the node x1 instead of the x0. So it doesn't make a difference, okay? But we will have a simplification in terms of the notation. So basically, we are having the nodes as x1, x2 up to xn. So we aim to determine a polynomial. Let's call that Px, which is such that when you evaluate P at any of the xi's, this is going to be yi. And if you take a derivative of the P and evaluate at xi, this is going to be yi prime. And this should hold for all I is equal to 1 up to n. Okay. So is the problem clear that what we are trying to do in the Hermite interpolation? That we are not just given the functional values, we are also provided with the derivative of the function at the same nodes. And we are trying to find another polynomial, a new polynomial, which will just not interpolate f, but the derivative of the p is also going to interpolate f prime of the derivative of f. Okay. So first of all, let's try to realize the degree of this polynomial, that like we did it in the case of the Lagrange interpolation, right? That what is the degree of the polynomial which we expect that we will be able to determine uniquely. So how many conditions we have here? So if we call this equation number, so let me start with 1 again, because I'm starting a new section, Hermite interpolation. So let me start with 1 again. Okay, so how many conditions we have in the equation number 1?
2n.
So these are, we have 2n conditions, right? So using the 2n conditions, what is the polynomial degree which you expect that you will be able to determine uniquely? So because you already know the form of a polynomial, right? So how many, so what is going to be the degree of the polynomial? At least we should look for, which we can determine uniquely using these 2n conditions.
2n minus 1 less than
2n
equal to 2n minus 1.
Right, so at least on the degree front, we have some idea that we should be looking for a polynomial of degree less than equal to 2n minus 1, because we have the 2n conditions and we hope that we will be able to determine the polynomial of degree less than equal to 2n minus 1 uniquely, right? So basically what we are going to do, we look, let me write this, so we look for a polynomial of degree at most 2n minus 1 or less than equal to 2n minus 1. Okay, so for that reason, I'm just going to denote this, and let me write it here itself. So I'm going to call this polynomial as p2n minus 1, p2n minus 1. That is, I'm adding in the subscript, I'm adding 2n minus 1. Okay, so as we have done in the case of the Lagrange interpolating polynomial, or when the data is given to be just the functional values. So we first establish the existence and uniqueness and then try to find the explicit form of such polynomials. So let me state this as a theorem. So we can prove that there exists a unique polynomial of degree less than equal to 2n minus 1, satisfying the interpolation conditions given in 1. Okay, unique polynomial, let's call it p2n minus 1. Okay, so let me skip writing it. We'll write it directly in the proof. So let's try to prove it. So first, I'm going to do the existence part. That is, we will show that there exists a polynomial satisfying this condition 1. That is, it will coincide with yi's at the xi's and its derivative will coincide with the yi prime at xi's. Okay, so we aim to show that there exists a polynomial satisfying equation 1. Okay, so again, the idea will be same, that I'm going to directly construct one such polynomial which will satisfy the conditions given in 1. Okay, and the polynomial which we will be aiming to construct will have the degree 2n minus 1. So I'll just do a little rough work just to motivate it, and then I'll write down what is an output we get here. So what we just try to recall, what we like, if you try to recall the Lagrange form, how did we write P and X? So what is the form of the Lagrange interpolating polynomial? It is yi times Lix, right? I is ranging from, suppose in this case, when we have the nodes from 1 to n, we will have I is ranging from 1 to n, right? And Lix were basically basis polynomials. So if we could construct the basis polynomials, then we directly had that any polynomial P and X is just written as a linear combination of these basis polynomials, right? So that is what we will try to aim here. So if we can construct the suitable polynomials, which are basically going to be a basis polynomials, then we will be able to write any polynomial. So that is what we will aim here, that I can write my P2n minus 1x. Suppose I could find some polynomials uix and vix suitably. We'll see what conditions we need for these polynomials, so that I can write my P2n minus 1 in this way. Yi times uix, I is ranging from 1 to n, plus yi prime times vix, I is ranging from 1 to n. Okay. So what properties we should seek for the uix and the vix here? So uix, vix, both are, first of all, they are the polynomials, right? And what they satisfy, that if we want my P2n minus 1 at xi should be yi, and P2n minus 1 at prime at xi, that should be yi prime, right? This is what we seek for P2n minus 1x. So what should my uix satisfy for me to have this? So if I evaluate at any of the xi, right? So note that here, what is the property for the Lix we had? We had that Li, if you evaluate at any of the xj, this was 0 if j is not equal to I, and it was 1 when j is equal to I. So that when you directly substitute x is equal to xi here, only term left in this summation will be, only non-zero term will be when when I is equal to, okay, so let's take here xj. So only term which will be remaining in this summation will be when I is equal to j. That is, you get it as yj, right? So likewise, I will be seeking for my uix that it should satisfy that when I evaluate it at any of the xj, it should give me delta ij. That is the same property what we have for the Lix. So this is for I and j ranging from 1 to n, right? And also, since we want this property to hold, right? So this means that I should also expect that when I take a derivative of my ui and when I evaluated any of the xj, this would give me 0 for all ij, right? So these are the property which I will be seeking for ui. Likewise, for vi, what are the properties which I should seek so that I can have these two conditions to hold directly? So if I construct my vi in such a way that if I evaluate vi at any of the xj, this is going to be 0 for all ij ranging from 1 to n, right? And if I take the derivative of the vi and evaluate at xj, this will be delta ij. So if we see, suppose we are able to construct our ui and vi in such a way that these properties holds, then can you see that we get the polynomial p2n minus 1 to satisfy these conditions? So are you guys following me? Are you guys with me? Is it okay so far?
Yes, ma'am.
Yes, ma'am.
Okay, so now we will be aiming to construct our ui and vi such that these conditions holds, because we know that if we could have our ui and vi in such a way that this will hold, then I can have, when I will substitute x is equal to xi here as an output, I will get yi from the right hand side, right? And if I take the derivative of the p2n minus 1 and then substitute x is equal to xi, then I will get as an output as yi prime, right? Using these properties. Okay. So now what we have to see that whether we can construct such polynomials ui and vix which are going to be of degree less than equal to 2n minus 1, which has to satisfy these conditions. Okay. So again, I will be using these polynomials Lix because I already have this in my hand, and these polynomials have similar properties what we are aiming for our ui and vi, right? So what we have that if I evaluate li of any of the xj when j is not equal to I, we know that this is 0, right? And what do we want? Let's try to focus on the ui first. So for ui, we want that when you evaluate this, for j is not equal to I, this should give me 0, right? And when it is equal to I, then this would give me 1, right? Another property which I seek for UIs is that this should be 0 even for the case when j is not equal to I, and also 0 for j is equal to I. That is, it is identically 0 for all I and j. Okay, so first I'm just trying to take care of the part when j is not equal to I in both the cases. Okay, so I'm trying to write the form of the UIX now. So when j is not equal to I want that ui at xj should be 0 and ui prime at xj should also be 0. This means that for all j not equal to I, this factor x minus xj, this is basically your xj is going to be a double root for the ui, right? So this means that it has to have this factor for all j is not equal to I, which basically says that I'm going to have Lix as the factor coming twice, right? Take a star of this, when is at xj. So I'm going to choose this, right, as the factor. So what is going to be the degree of this? So for this data, we have the data ranging from I is equal to 1 to n. So what are the LIX here? So these are product of x minus xj. J is ranging from 1 to n. J is not equal to I. And this is divided by xi minus xj. So what is the degree of the polynomial LIX?
n minus 1, ma'am.
N minus 1. And I'm having two factors here. So this degree is going to be 2n minus 2. Right? So only possibility I can have here as a factor is a linear polynomial. Right? So I'm just going to take some Rx times Lix square, and this can be a linear polynomial because I want my UAX to be a polynomial of degree less than or equal to 2n minus 1. Okay. So note that if I take my UAX in this way, already my these conditions are satisfied and these conditions are satisfied. So only the two conditions which I need to check is that ui at xi should be 1 and ui prime at xi should be 0. Okay, so Rx is a linear polynomial, so you can take any general polynomial, say alpha plus beta x, right? And what you have to do to determine these constants alpha and beta, you just verify that ui at xi should give you as an output 1 and ui prime at xi should give you 0. So these two conditions you have it and you just simplify it and you will be able to determine alpha and beta. Okay, so I'm directly writing what you get as an output. 1 minus 2 into li prime xi into x minus xi multiplied by lix square. That is, this is what you will get it as Rx. So this you have to verify. Okay. And you can clearly check that if you take ui at any of the xj, so if you so what will happen to this will give you delta ij, and when if you let's take j is not equal to I, then clearly this is 0. And if you evaluate ui at xi, so at xi this will be 0, right? Because you have a factor x minus xi. So only term which will be left is that ui at xi is nothing but li of the xi squared. So li of the xi is 1. So you will get this as 1, right? That's a quick check. And if you take a derivative of this ui, so what it will be? So 1 minus 2 li prime xi x minus xi, and the derivative of this is going to be 2 lix li prime x, right? Now the derivative of the first term is going to be minus 2 li prime xi times lix square. So if you substitute any of the xj, j is not equal to I, so you can see that lix is sitting as a factor in both the terms, right? So at any of the xj, it is going to be 0 when j is not equal to I. And when j is equal to, when you take x is equal to xi here, then this factor will be 0 and li of xi is going to be 1. So you will get minus 2 of the li prime of the xi from here and then plus 2 from here and minus 2 of the li prime of the xi from here. So this will be 0. Okay, so that's so we also have that ui prime at xj, this is equal to 0 for all j, and this holds for all I and j ranging from 1 to n. Okay, so I'm forming these polynomials for all i's ranging from 1 to n. All right, so uix is okay. Now let's focus on the vix. So again, if you observe that vi, I want that it should be 0. So if we take the case j is not equal to I, I want that vi at xj should be 0 and vi prime at xj should also be 0. Right? Whenever j is not equal to I. So this means that again I'm going to have one factor as Lix square for the Vx. So Vx will also have Lix square as one of the factor, and then the choice we can have as a multiple is a linear polynomial. Okay, and you determine these linear polynomial. Let's call it say Cx plus D, and determine C and D such that, sorry, this is Vi, such that Vi at x observe. So I'm just going, this is just going to be x minus xi. Vi evaluated at xi will be 0, and its derivative and substitute x is equal to xi, then this is going to be 1, and upon differentiating you will not get anything from here. So you can verify that this Vix this will satisfy Vi at xj, this is equal to 0. So again I'm constructing them from all the I ranging from 1 to n. Okay, and this holds for all j is equal to 1 to n. So this is equal to 0 clearly because Lix is satisfying that property, and when x is not equal to j, then this is going to be 0, and when x is equal to xi, this term will be 0, right? So clearly this is getting hold, and you can find what is Vi prime of the x. So this will be Lix square plus x minus xi times 2 Lix into Li prime x. So again, you can verify that Vi prime at xj, this is delta ij. Okay, so thus we have got ui and the Vi. So we can have the p2n minus 1x as summation of yi into uix, I is ranging from 1 to n, and yi prime into vix, I is ranging from 1 to n. Okay, so what we have established, thus the existence of Hermite interpolating polynomial is established by taking p2n minus 1 as this, right? And we will be proving that this polynomial is going to be unique. Okay, that is, we will prove that there exists only one such polynomial which can satisfy the interpolation condition 1, and which is going to be of degree less than equal to 2n minus 1. Okay, so, but let me say what I'm going to call this polynomial as. I will use the notation hnx for this. Okay, that is hnx, I'm going to set it as this p2n minus 1x, which we have found here. Okay, and this is known as the Lagrange form of Hermite polynomial, Hermite interpolating polynomial. Okay, so basically we have also got the expression for the polynomial, but once we have shown that this polynomial is unique, then of course we have the formula to determine such polynomials, right? So let's talk about the uniqueness part. So this I will ask you to complete. Again, you take two polynomials, say p2n minus 1x and q2n minus 1x. Okay, and these both the polynomials satisfy conditions of degree less than or equal to 2n minus 1, right? And then you can form a new polynomial by taking a difference of these two polynomials. Okay. So using the interpolation conditions, what you will be able to observe? You will be able to observe that this polynomial has xj's as the zeros for all j's ranging from 1 to n. Not just that, you will be able to conclude that the derivative of the d2n minus 1, this is also going to vanish at all the xj's, right? So this will say that, so what can you conclude using these two conditions? That each of the xj is a double root for this polynomial, right? This means that you're going to have x minus xj square as a factor for each j, which means that you will have x minus x1 square, x minus x2 square, up to x minus xn square as a factor of the d2n minus 1. So the d2n minus 1x will be some other polynomial, let's call it say hx times this, right? But so d2n minus 1 is a polynomial of degree less than or equal to 2n minus 1, and it is going to have at least 2n zeros, right? So what does it say? If you use the fundamental theorem of algebra, so if d is a polynomial of degree less than or equal to 2n minus 1, it can have at most 2n minus 1 zeros, counting with the multiplicity, right? So this is again the same argument what we had used in the case of the Lagrange when we were getting the Lagrange form of the interpolating polynomial. That time we proved that using the similar arguments, that how do we show the uniqueness of the polynomial, right? So you just complete the arguments and you will be able to prove that d2n minus 1x, the only choice you can have for this polynomial is a zero polynomial, which will imply that p2n minus 1x equals q2n minus 1x. This means that the Hermite interpolating polynomial is unique. Okay. All right, so since it's already 5, so I will stop here, and if there are any questions, I will take it in the next class. Okay, so I'm just ending the meeting here because I have another class now.